Hi, what I've got now is an energy problem that's kind of a difficult problem, but on the easy end of difficult. So a medium to hard problem, let's say that. The problem reads, a 2 kilogram package slides along a floor with speed 14 meters per second. It then runs into and compresses a spring until the package momentarily stops. Its path to the end of the spring is frictionless, but when it's compressing the spring, there is a kinetic friction force from the floor with a coefficient of kinetic friction of 0.45. The spring constant is a whopping 10,000 newtons per meter. That's a pretty stiff spring. By what distance d is the spring compressed when the package stops? All right, what do we have? We have a spring and a package coming at it. So this bit is frictionful, if that's a word, frictiony. And then the package is going to compress the spring and be momentarily at rest. So we do have some initial velocity. Here it's momentarily at rest. We want to know what is the distance that the spring was compressed. This is still frictiony, so I'll do that. What do we know? We know the mass is 2 kilograms. Its initial velocity is 14 meters per second. And the spring constant was 10,000 newtons per meter. Coefficient of kinetic friction, 0.45. I think that's all we've got. All right, we've got a picture, we've got our knowns. Now I'm going to say this is my initial condition, this is my final condition, my object is the box. Okay, now we do our conservation of energy. Initial energy plus minus work equals final energy. In the initial condition, is something moving? Absolutely. So we have initial kinetic energy. Is anything above its lowest point? It never changes height at all. Is there a spring? Yes. Is the spring compressed initially? No. So it starts just with kinetic. Final energy, final. We're not moving, so no kinetic. We're still at our main level, no height change. And now we do have a spring compressed. Okay. And is there any work being done? To answer this, we do a force diagram of the box as it's compressing the spring. Normal, floor pushing up. We've got the earth pulling down. The spring is pushing back on it, and as it's moving this way, friction's opposing the motion like that. Is there anything pushing the box forward? Is there forward force at all? No, there's nothing pushing on the box in that direction. Both forces are that way. What's the direction of motion? To the left. Okay, so now what causes work? What does work on the box? Here's my direction of motion, that's perpendicular, it's these two. But, as you remember, with a very similar problem, we never talk about the work done by a spring because we've taken it into account right here. So we have work done by friction, and that is negative. Those are opposite directions. But we do not include the work done by the spring because we're already taking into account that change in energy right there. All right, 1/2 mv initial squared minus friction times distance equals 1/2 k delta x squared. There is our equation. What are we looking for? We're looking for the distance. What do we know? I know the mass. I know initial speed. I don't know that. I know that. I don't know that. Okay, so I need to figure out what the friction force is, and I need to know what delta x is. Well, friction force, friction is mu times n, and what is the normal force in this case? It is equal to mg. So friction is mu mg. All right, so I can replace that friction there with mu mg, v initial squared minus mu mg times d equals 1/2 k. Now I still need to know delta x squared. What is delta x? Delta x is the compression of the spring. So it's how much the spring got compressed. Oh, wait a minute. That's what I'm looking for. It turns out that the distance traveled along the frictionful path is the same as that. So D equals delta X, which means I can erase this and replace that delta X with a D. Don't forget, it's squared. Okay, now, do I know everything? I know mass, I know V initial, I know mu, I know M, I know G, looking for D, I know K, I'm looking for D. Ta-da! Okay, so why is this a medium hard problem? This is exactly like the one we solved before, isn't it? This is exactly the equation we had before. Well, this is harder because it's mathematically harder. I have a D squared, I have a D, I have a non-D term. What does that mean? Quadratic. So, let's see here, 1/2 K, 1/2 of 10,000. I have 5,000 D squared. I'm going to bring this D term over, which makes it a positive. Mu mg times D. So what number is that times D? 0.45 times 2 times 9.8. I'm not doing that in my head. 8.82. 8.82. And then bring this term over. It becomes a negative. 1/2 mass. 1/2 of 2 is 1. Velocity squared. So 14 squared. 266. 196. There we go. So there's my equation for the quadratic, and okay, so D would equal negative B plus or minus the square root of B squared, 8.82 squared minus 4 times A, 5,000 times D, negative 196. Oops, wrong one. There we go. All over 2A, that'll be 10,000. Okay, so at this point, grab your calculator, give it a try, see what you get. And again, you'll have two answers, one of which will probably make physical sense, one of which probably won't. When I did it, my two answers were plus 0.197 and negative 0.199. So, that would not make sense. This does. So the distance it travels compressing the spring is 20 centimeters. Is that reasonable? Sure. For a 2 kilogram box, moving pretty darn fast. 20 centimeters with a really, really stiff spring. So it's moving fast, but it's a really stiff spring. I think that's reasonable. So there we go. Another force problem. With springs involved and kinetic energy, and again, that sneaky little, got to remember that those two are the same. So that makes it a little bit harder, and the quadratic makes it a little bit harder. So that's why I'm calling it a medium hard problem. Hope this makes sense. Good job for watching.